Welcome. Critical chain is one of the most important ideas in project management. Many adopters of critical chain project management have reported huge reductions in project completion times. This video presents two critical chain models. Both are stochastic or probabilistic models where judgments about uncertainty are expressed as distributions. Monte Carlo simulation calculates the forecast time to complete as a distribution. I'm John Schuyler, a decision analysis consultant and trainer. In 1992, I was invited to write an article about decision analysis for project managers. This led to an eventual 18 articles in PM Network magazine. And these articles were the foundation for two best-selling editions of Risk and Decision Analysis in Projects, published by Project Management Institute. This video is an online supplement to the third edition. Eliyahu Goldratt was a physicist who became famous for his theory of constraints. The operable constraint is often a bottleneck. His process is, in summary, 1. Find the current constraint. 2. Exploit the bottleneck resource. Keep it busy or fed. And, if feasible, expand its capacity so that it is no longer constraining throughput. 3. Repeat. Goldratt is a legend in manufacturing. His most popular books are The Goal and It's Not Luck. Goldratt's books have sold over 4 million copies, translated into 23 languages. The first edition of Critical Chain was published in 1997. This might be the most important book ever published about project management. It is an engaging novel and easy read. I recommend this book to everyone in project management. The most recognized constraint in a project is the schedule critical path, abbreviated CP. The critical chain adds to the critical path to include resources working on critical path activities. Most interesting is that the critical chain may include activities that are not on the critical path. As you will see, there are additional constraints that we ought to include on the critical chain. As you found this video, you may already have known all or most of this. Let me take a minute to go over some terms that may be unfamiliar. The central concept in decision analysis is expected value, EV. This is synonymous with the mean statistic, used so often in probability analysis. Expected value is the probability-weighted average of all possible outcomes. In Monte Carlo simulation, typically 1,000 or more trials or iterations are performed. Every case is equally probable, so the average or sample mean approximates the solution expected value. PXX notation is popular in project management and in cost estimation. With schedule, P90 means the time estimate where you are 90% confident the actual time will be less. For me, the key ideas in critical chain project management are padded single-point time estimates. People are conservative, intending to assure a high probability of task or activity's success. Slack before the activity begins gets wasted. In the book's teaching analogy, students procrastinate and avoid working on an assignment until it is almost too late to begin. However, especially on a job, remaining time is not returned and therefore unavailable for other activities. If properly estimated as a distribution, the time to complete an activity might be judged as this blue curve. However, because early completions tend to be not reported or underreported, the as-reported distribution might look like this red curve. The red curve's left side will be even more abrupt if there is a target completion time. A budget is almost always consumed. Time remaining may be used for organization or other non-project matters. It is consumed and not reported. Even if more appropriately dedicated to the activity, the extra time will be used to enhance or gold plate the work product. People tend to multitask, losing focus and concentration. Multitasking is inefficient and leads to errors. Activity work should receive full attention for the duration. This figure illustrates Goldrat's presumption that most single-point activity time estimates are conservative. The path is a sequence of activities in parallel with other activities or paths. In typical estimation, people conservatively judge time to complete for each activity, say at a 90% confidence level. An objective, meaning unbiased, activity time estimate would be an expected value or the mean statistic. The shaded P90 minus expected value difference is padding or safety. Padded activity times are like having buffers after each activity in the path sequence. We could rearrange, placing the collective padding at the end. Because it is very unlikely that reasonably independent activities would all be late, collecting all the padding for an end-of-path buffer would be excessively pessimistic. Reduce the buffer time so the path is still highly confident, say P90, sufficient to protect the follow-on starts at a merge point. Monitoring consumption at the end-of-path buffer is a key project control tool. We now appear to have slack on this path sequence. I've illustrated activity A starting as late as possible. Premature activity finishes are analogous to manufacturing work in progress, which Goldrat hates. We can model whatever scheduling logic we think is appropriate. In my model, competition for the resource and its availability are important. So I will mostly use ASAP logic. Begin as soon as possible. However, a scheduling tool is to safely schedule activities' earliest starts. An activity can start as soon as predecessors finish, other schedule constraints are satisfied, and the resource is available. This video demonstrates two critical chain simulation models. Both use Monte Carlo simulations so that we may incorporate activity time estimates and other parameters as probability distributions. A simple Excel model shows critical chain calculations similar to critical path method. Recalculating the spreadsheet demonstrates the critical chain changing under uncertainty. There may be competition for a resource from other project activities. Gantt charts illustrate the activities schedule and reveal the critical chain. I once saw an Excel animation demonstrating critical chain. That demonstration gave me a greater appreciation for the power of critical chain. I hope this video will do the same for you. Though I often program in Visual Basic, I'm not a power Excel programmer. For the more robust model, I decided to use a high-level programming tool, MATLAB, instead. MATLAB has excellent charting capabilities suitable for the project animation. I also licensed 2 optimization toolkits. There's little restriction on how much real-world detail that is possible with the MATLAB platform. We can determine planned activity starts with mathematical optimization. 2 features that we will see in the second simulation. Other projects and customers compete with our project for resources. A resource can be reserved for a fee. The project model is moderately complex, though it can be extended to most any level of detail. Let's first look at a spreadsheet model of critical chain. Setting up a small schedule model in Excel is not particularly difficult. Here is the basic model. The same model is expanded on another worksheet to operate with the at-risk Monte Carlo simulation add-in for Excel. On this first worksheet, we can explore the model without at-risk. Let's start with the table in the upper left. I've used triangular distributions to represent judgments about activity completion times. These are popular because they are so easy to use. The triangular distribution is uniquely specified by 3 parameters: low, most likely, and high. For our purposes, assume activity completion times are independent. The expected value or mean in the case of a triangular distribution is simply the average of low, most likely, and high values. Skewed equals 0 means the triangle is symmetric. Skewed equals 1 just means the distribution is not symmetric. There's a longer tail on the right side. Excel's random number function, rand, is in each of these Rn cells. Sample or trial values for activity completion times are in this next column. The random number is the pxx value. For example, for activity 1, 5.07 weeks is about p14. There is a 0.143 chance the activity duration will be less than 5.07 weeks. The distribution sampling formula is near the slide bottom. While appearing complex here, the formula is rather simple as written in textbook form. Using the activity trial values shown, we have these trial values for activity start and finish times. This is the chief outcome cell, time for project completion. This trial shows the project finishing in 68.8 weeks. Running a 10,000 trial Monte Carlo simulation produces a sample mean or average value of 62.486 weeks. This is our best estimate of project completion time. Assuming our judgments for the activity completion times are unbiased, the sample mean is our unbiased estimate. Monte Carlo simulation is an approximation method. More simulation trials, that is, more synthetic data, produces more precise answers. I'm representing the precision in the expected value completion time calculation. Of course, there is nowhere near this precision in the judgments and model detail. We typically round probabilistic forecasts to 2 digits, such as 62 weeks. Here is the critical chain sequence from a calculation below. For this trial in the Monte Carlo simulation, the critical chain is activity 1, activity 4, activity 3, activity 8. Pressing the F9 recalculation key generates a new simulation trial. I'll step through a couple for you. Notice how the random numbers and triangular distribution samples change with each F9 press, and most other numbers change as well. This one is a bit more interesting. Activity 6 has to wait for its predecessor, activity 4, to finish. In this trial, the WOG in the critical chain indicates waiting on green. This means that task 6 had to wait longer until the green resource finished performing activity 2. The right columns have formulas for activity start and finish times. The calculations are very similar to critical path method. The formula logic is from the precedence relationships in the work breakdown structure. The finish to start relationships are also clear in the activity network diagram. The only addition is recognizing that an unavailable resource can delay the start of the next activity for that resource. Here again is the overall model without at-risk. Let's look at the network diagrams on the right side. The upper network shows the activity start and finish times. At the right side of an activity label, there is sometimes a small c. This means for the recalculation that the task is on the critical chain. The network diagram at the bottom is from the more elaborate critical chain model that we will see later. Let's use it to follow the critical chain. Let's traverse the lower network diagram for the last trial. The critical chain is activity 1, activity 2, waiting on the green resource, activity 6, followed by activity 7, and finally activity 8. Here is a Gantt chart. It is easy to pick out the critical chain from this graph. Working backward, activity 8 begins when the activity 2, activity 6, activity 7 sequence completes. Activity 2 starts when activity 1 finishes. The WOG, waiting on green, identifier isn't necessary here. However, identifying gaps between activities will be useful in the more comprehensive model later. Here is the at-risk simulation model on another worksheet. At Risk is a highly popular add-in to Microsoft Excel for Monte Carlo simulation. Red cells identify output cells, and the green cells contain a statistic from the corresponding output cell, most often the sample mean. In the center of the worksheet is a shrunken image of the project duration distribution. Let's look at the lower left portion. Here is where I've determined which activities are critical. Of course, start and end activities are always critical in this network. This is a probabilistic model with uncertain values. The critical column has ones for activities when they are on the critical chain. Again, with this activity network, activities 1 and 8 are always critical. One of the most interesting and useful features is the critical index. Critical indexes are the average of the cells in the critical column. CIs for activities 2, 3, and 4 are most often critical, and this information is useful in guiding risk mitigation efforts. The WOR.C column indicates when an activity is waiting on a resource not being used by one of the activity's predecessors. The dot is common probability notation for AND. Values in this column are ones when the activity is critical and it is waiting for its resource to finish another activity. When activity 6's predecessors are complete, it is waiting for the green resource to complete about 10% of the time. Now we're finally ready to look at the animated critical chain simulation. This is a more realistic project model and an animation of the critical chain. For lack of creativity at inception, I named it ProjOpt, short for Project Optimization. This animates a project execution and highlights the critical chain. Though I do a lot of programming in Visual Basic, I didn't want to work in Excel for this animation project. I chose MATLAB, a well-established tool with over 1 million users worldwide. It is a high-level programming language with syntax similar to BASIC. MATLAB features functions, scripts, subroutines, and data structures. The platform has detailed charting functions, which I'm using for animation. There are toolkits for optimization, machine learning, and many other applications. ProjOpt is comprised of 17 modules involving over 2,000 lines of executable code. We discussed these figures earlier in explaining Goldrat's view in Critical Chain, the book. While as late as possible is an ideal, this is awkward when using a probabilistic project model. Because activity duration assessments are distributions, we don't know the duration of this chain sequence. Also, there is no simple way to determine a start date for activity A under uncertainty. In ProjOpt, I want to optimize decision variables. These include activity planned start times. Monte Carlo simulation allows us a way to calculate with probability distributions. Though not illustrated here, there is uncertainty about when all predecessors to this path are complete. If predecessors complete before a successor activity is ready, there is a delay in assembling workers and materials. Similarly, workers and materials may be in place to start an activity before all the predecessors are complete. Then there is the cost of an idle crew and perhaps unnecessary site congestion. There are no express buffers, though normally there will be planned gaps between activities. In addition to planning activity starts, some resources may allow, at a cost premium, reserving blocks of resource time. Timing and durations of these reservations, if used at all, are additional optimization parameters. My model assumes outside resources. Of course, resource managers want to optimize their operations and have their own priorities and scheduling rules. Our project activities compete with others for these resources. So, considering all this, the critical chain can be substantially longer than the critical path. The project is a simple activity network, the same as shown in the Excel model. There are again 8 activities or tasks, and 3 resources, now labeled A, B, and C. Red outlines indicate activities in process. Their corresponding resources also have red borders. Upon completion, connections to successor activities become thick green lines. Activity borders turn green. There's competition for resources from three sources: other activities in our project, other projects in our company, and jobs performed for other companies. Here are some features that you will see in the PROJOB simulation. Self-imposed constraints on an activity start. If simply waiting for the predecessors to finish, the activity has one or more incoming black connecting lines. These connections turn to heavy green lines when the predecessor activity completes. The left end of an activity box will sometimes have a small red constraint box. During the trial process, these constraints are, in effect, keeping the activity from starting. After the project is complete, the constraint box shows whether the constraint was ever in effect. During the project, a small C in the upper left corner means there is a planned earliest start date constraint and the calendar has not yet reached that date. During the project, a large letter in the lower left corner, A, B, or C, means the activity is waiting for this resource to become available. There may be other constraints not represented, such as available workspace and weather. Moreover, activities may use more than one resource, and some resources, such as computers and deeply staffed services, lend well to sharing. The top of the screen will show resource statuses and jobs in queues. Below that is a Gantt-like chart showing the resource histories, our activities, not our project jobs, downtime, and idle. I'm going to take you slowly through a single trial of the PROJOB simulation model. During a Monte Carlo simulation with many trials, the animation is turned off for speed. When the animation is on, this is the initial figure at time 0. In the center of the screen is the activity network diagram, same as we saw in the spreadsheet model. Each activity requires only one resource, one of A, B, or C at the top. These resource letters supplement the background colors. A resource can work on only one job at a time, no multitasking. An activity or job started will be pursued without interruption to completion. My model assumes that we contract outside resources to perform activities. Resources have scheduling rules, and we will sometimes find the resources unavailable. Activity 1 starts the project. When a resource is performing an activity for our job, both the resource and activity borders will be red. Below the resource boxes are status indicators. The working on status may be a project task number, NP job for a non-project job, downtime, or idle. Project queue lists the activities with completed predecessors. An activity in queue will launch when any calendar constraint is satisfied and the resource is available and there are no other non-project jobs in the queue. The NP job queue row indicates the number of non-project jobs waiting for each resource. The in reservation row will show a Y for yes when the resource is reserved for our project. During a reservation, no non-project jobs will be allowed to start. The Gantt chart has two sections. The upper section shows what is happening with each resource. When a colored bar with a number appears, that indicates an activity now in process. The time to complete is sampled and ends the bar. The project team knows the estimated time to complete distribution, but not the actual completion date. However, the computer knows, and that duration is what the bar length represents. The lower chart section is a plot of reservation periods. For a fee, we can have the resource block out periods so as not to start non-project jobs. Then one of our project's activities can start when ready. Shown are 3 reservations. I put in 1 for each resource. Another project planning option is to set earliest activity starts. This will limit premature activity finishes, yet allow sufficient end-of-path buffers before merge points. An earliest start constraint is indicated by a vertical red bar on the resource line. Our plan is to not start Task 5 before 27 weeks into the project. I've stepped the simulation to the arrival of a non-project job for Resource B. The arrival is indicated by a black circle. When a non-project job commences, a black line indicates its duration, as shown here. Note the time pointer has advanced to 2.410 weeks. The cumulative project cost is indicated at the right. The next event is the finish of the non-project job with Resource B. The resource immediately goes into a 1-week downtime period. My resource model assumes that the resource staff work diligently and exclusively on a single job until completion. That job might be one of our project activities or a job for another customer. After completion, the resource team shuts down for 1 week to catch up on training, equipment maintenance, etc. Now, Resource B's downtime period has ended, and the resource is idle. Now, Activity 1 finishes. Its border turns green, indicating that it has finished. Activity 1 is a predecessor for Activities 2 and 4. The lines to these successors are now green. As the resources for these activities were both idle, Activities 2 and 4 launch immediately. Their borders turn red while in process. The green 2 and yellow 4 bars indicate their durations. The bar ends are actual finish times, though, again, this information is not known to the project team. I'm now going to step ahead about 10 events so that we can see a different situation. I stopped here to point out 3 constraints in effect. The B and C resource letters in the lower left of activity boxes indicate that activities 3 and 6 are waiting on their respective resources. Activity 5 has an earliest start date constraint, so this activity is waiting on the calendar. The vertical red bar with 5 beside it marks the planned start no earlier than constraint. The activity box indicates this with a small c in the upper left corner. A constraint indicator disappears when the constraint is satisfied. After the trial ends, Project will determine the critical chain. The read-to-run network will show which constraints delayed individual tasks. The next event is Resource C's downtime finishing, so this resource is now available. Activity 2 finishing is the only predecessor for Activity 3. As C is reserved for our project, just barely, Activity 3 now launches. See the 2 black circles on Resource C's timeline? The 2 non-project jobs are in a queue and must wait because of the reservation. The clock or calendar is now at the earliest start date for Activity 5. Fortunately, Resource A is available, so Activity 5 launches. I'll skip past several events. You may pause the video at any point if you wish to examine the figure. Notice that Resource A has performed 3 non-project jobs in succession. Another has arrived, but it cannot start because we have reserved Resource A. Activity 7 finishes, which enables the final Activity 8 to begin. And the project finishes at 67.4 weeks. A red underscore highlights the critical chain. Note that the expanded critical chain notation contains more information, especially about the delays with Resource B. This final activity network diagram for this trial shows the critical chain highlighted in red. The critical chain for trial 1 is Activity 1, Activity 2, downtime for Resource B, a non-project time for Resource B, downtime for Resource B, Activity 6, another downtime for Resource B, Activity 7, and Activity 8. Resource C, working on Activity 4, delayed the start of Activity 3, but this did not affect the project completion. Activity 5 start was intentionally planned to start no earlier than 27 weeks, and the small c indicates this active constraint. I'll rerun the simulation without interruptions with half-second pauses after each event. Here's another critical chain. This time, activities 2, 6, and 7 are each delayed by Resource B performing several non-project jobs. I'll rerun for a third trial. Let's wrap up with key points. CCPM, Critical Chain Project Management, is one of the great ideas in project management. As with many inventions, it is obvious in hindsight. The motivations are not as pure and simple as in Critical Chain the novel portrays. For example, activity time estimates might instead be optimistic because of political pressures or motivational bias. Simple resource loading is an inadequate representation. A key reality is competition for resources. Resource managers have their own objectives and policies. There is a large body of knowledge about modeling and optimizing resource policies. Accepting reservations, Projopt uses a simple first-in, first-served policy. However, modeling resources can have complexity comparable to modeling projects. Uncertainties abound. Decision analysis is about decision-making under uncertainty, and those decisions are based upon estimates. We capture expert judgments about risks and uncertainties as probabilities and probability distributions. Monte Carlo simulation allows us to do mathematical operations on distributions. Dynamic project modeling is most interesting when the critical chain changes among simulation trials, and the model outcomes are distributions. Modern PCs can easily accommodate even high project complexity. Thank you for watching this video. If you are interested in risk policies, there are 2 remaining videos in this series. The URL in the middle links to these resources and more. Also, there are books, software, and other general DA resources. I welcome questions about DA or the software. Also, please send along any suggestions to improve these materials. Again, thank you for watching.